go on with our next presentation, and we have a tandem again for this presentation. Welcome Nico Weber on stage. You are a candidate for a PhD at Opel. That's great. And you are accompanied by Philipp Rosenberger again. We have met you this morning already, and you will talk about the simulation credibility layers, especially towards a holistic assessment. And that's incredible. The stage is yours.
Thank you, Laura. So, dear audience, and especially dear virtual participants, on behalf of the partners and the work packages involved, I would like to welcome you to our talk on the different simulation credibility layers and what we as Z-Level project are proposing to get a little closer to holistic assessment of the same. In relation to the already known football illustration, which summarizes the different fields of work within Z-Level, our activities can be assigned to the development of methods for the credibility assessment of models, as well as the simulation architecture. Additionally, these activities are directly related to the interesting presentation which we had the chance to listen to this morning from Hans-Martin Heinkel on the credible simulation process. The focus of this morning talk was on the why and the how the credible simulation process can support specifying, designing, implementing, and qualifying the simulation tools and models needed for a given simulation task. In the following 20 minutes, we will really focus on the what, meaning an explanation what credibility really means and how the proof of this credibility can be done in principle. For that, we elaborate on different credibility layers, since from our point of view, the assessment of the overall credibility of an automated driving system simulation environment can be structured into verification and validation activities on different levels. As you can see on the slide, these are called as model level, as coupling level, and simulation platform level, which at the end provide all evidence for the credible simulation process, which is wrapping around all these layers. So let's take a deeper look at the first layer, which deals with model credibility in the following. I think all of us would agree that using simulation-based methods is inevitable for the safety validation of automated driving systems. However, the intrinsic challenge which arises through that is the fact that additionally to the actual goal of validating the safe behavior of the automated driving system, this requires a validation of the results generated by the models and simulation itself in advance. And as we on top know that ADS-equipped vehicles are highly complex systems operating in an even more complex environment, including the multimodal interaction with third persons, the question arises, do you trust in the results of your models and simulation? And if yes, why? Taking a look at the literature, scientific community, or organizations like the NASA or the American Society of Mechanical Engineers, there is a thorough discussion about that topic. The term most often used for activities in this context is credibility of modeling and simulation. Model credibility refers to the decision maker's confidence in the model. One goal of the validation and verification process is to gain this credibility, for example, according to Carson. Credibility is the quality to elicit belief or trust in model and simulation results, according to NASA. Using these definitions as an example, two major challenges arise. First, determining the degree of credibility is a partially subjective decision that depends on many factors. Second, the decision on credibility depends heavily on the modeling and simulation user's perspective, the respective development task, and of course, the application purpose. At the end, the user will ultimately decide whether he or she trusts the model and the simulation results. So, of course, the question arises, what can be done to overcome these challenges and to reach that credibility? On the one hand, in our opinion, it's essential that the model developer and the model user interact during the overall model development and operational phase. Thereby, it is of paramount importance that both agree on the purpose for which the model is built and its underlying assumptions. Furthermore, the literature mentions various criteria like verification, validation, or data credibility to increase the trust in models and simulation, serving at the end the overall goal of objectifying this partially subjective process as much as possible to come to an overall credibility assessment. Based on these criteria, we can now have a deeper look how they interplay and how the interaction of these criteria among each other can be described. The main challenge here, again, is to objectify the process of creating credibility and to tailor the validation and verification activities to the specific intended use of the model. The interaction of these so-called credibility criteria can be illustrated within an abstracted decomposition of the modeling and simulation process. At the beginning of every modeling and simulation process, of course, there is the reality of interest. This reality of interest has to be captured, has to be described, and has to be agreed on by the model developer, but also by the model user to derive the conceptual model. At this point, we can see again that we need to have different roles involved and work together for these activities. This conceptual model can be described as the collection of abstractions, assumptions, and descriptions of physical components and processes representing this reality of interest. One part of that could be, for example, a state space model with predefined parameters and corresponding parameter value range, but not limited to that. The process of determining this model and the process of determining the degree to which a conceptual model or a model design adequately represents the reality from the perspective of the intended use is referred to as conceptual validation. This conceptual validation provides the first essential credibility criterion. For example, validation or verification techniques like phenomena identification and ranking technique can be carried out during this process step. For deriving a simulation model, in the next step, an implementation of the conceptual model has to be carried out. The simulation model then is represented by software code and is characterized by the ability to be executable with a specific solver tool. To prove if the conceptual model is implemented in the right manner, verification is required as the next important step to increase the trust in the modeling and the simulation. For this purpose, the simulation model has to be compliant with its requirements and specifications as detailed before in the conceptual model. As a result, verification represents the second important credibility criterion. Having the simulation model at hand then, experiments with respect to the intended use can be carried out. Thereby, the process of determining the degree to which an operational model, so the simulation model, is or provides an accurate representation of the real world, again, from the perspective of the intended users of the model or the simulation is referred to as operational validation. This builds the third important criterion for creating credibility in modeling and simulation results. And before I will hand over to Philipp, on the last slide of my presentation part, based on the previously explained criteria, I want to give an overview what we, with the different work packages involved, really derived exemplary results and what we have generated over the time and the course of the Z-level project. At the very beginning, we conducted a comprehensive literature review and state-of-the-art analysis, and we created a document which provides the theoretical basis for understanding the different elaborated deliverables. This document entails a thematic classification of verification and validation and their associated criteria in a higher level process for assessing the credibility of models. Based on this analysis, we propose a level-based approach for assuring the credibility of the respective model. The basic idea here is that depending on a required credibility level, different amounts of work have to be carried out regarding the fulfillment of the before-mentioned various credibility criteria for reaching a corresponding specified credibility level. Subsequently, we went through the jungle of available V&V methods and techniques and created the so-called method library. This library includes a categorization of different methods and techniques and assigns these methods and techniques to these credibility criteria so that a model developer knows which V&V method could be chosen to reach a specific credibility level within the respective criterion. To showcase this process and to make it even more explicit, we generated an exemplary validation report for a radar sensor model, which can be regarded as an exemplary follow-up step after selecting a suitable V&V method out of this method library. This report then in turn provides evidence for the last deliverable, which is the template of a credibility assessment report. This artifact includes a description of all activities and evidences that can be used to argue the overall credibility of a simulation model. Finally, the credibility report itself is then an important input artifact for the application of the credible simulation process. And with that, I would like to hand over to Philipp, who will now dive even deeper in the technical details and will show an operational validation of a LiDAR sensor model. Thank you.
Thank you, Nico. Welcome again from my side. It's not only that you have seen me already, also I've shown some details of the following presentation, and I think it's worth to repeat that. So before I start again, I would like to stress that especially the model validation, the LiDAR sensor model validation, was a collaboration between the both projects, Z-level and VV methods, and as Nico said, this is necessary that there is a collaboration between the model user and the implementer. So when we speak about this four-stepwise sequential process, and to repeat, you have to start again, of course, with collecting the sensor effects, so literature review, or what would be even better is to have a lot of different measurements at hand. You have to sort them in a tree-shaped manner. In this case, the pair collect tree. We did this actually, or we came up with this in the Z-level project to kind of start the overall activities for sensor model specification because as we started, we found there's no method available, and we need one to get started. And it's also a bit of a timing issue that the VV Methods project was a little bit afterwards started. So even if they used the model and actually had to specify it and did this exemplarily, we had to come up with something to get it started. So PerCollect is a collaborative activity actually, and we've put this on GitHub. You see this not only for LiDAR, also for camera, for radar. We would like to also add ultrasonic sensors as well. And again, you start with the phenomenon or phenomena on the top, for example, false negative objects, and you go down to not recognized or false negative detections in the point cloud, and then down to the causes and design parameters of the sensor. The next step, as I said, is to fill the cause-effect phenomenon relevance analysis, to conduct the experts for the sensor, to know the ODD, where the simulation takes place, all the different environmental conditions and objects that could occur. And you have to consult a system under test expert or expert group, and then you can derive and sum up both scores for occurrence and for impact, and you finally end up with the relevance scores. And as I said, we are very happy that actually the VV Methods project took this method and all the different steps and actually did this exemplarily and performed also the specification of a model based on this. If you would like to learn more about this, you can still visit the experts at the booth. The next step is when you have specified the model to validate it. And validation in this case means to compare real and simulated sensor data. So how is this done? What do you need? Of course, you need the data collection. You need to collect the sensor data, so in this case, the LiDAR data. You use tools that are very precise to know where was the sensor located, and you have to collect the reference data as well. For example, the distance to other objects, the object materials, and so on. In this case, for example, for the distance, a tachymeter was also used to have the high accuracy in the reference data that is needed. Then you need some metrics to compare the real and the simulated data. And in this case, when you speak about sensor data, it's not only to compare specific values and the scattering, but also you have to compare the scattering itself. So there's a model bias, which is the mean error between the simulated sensor data, and there's also the scattering error. So the scattering of the real sensor and the scattering of the simulated sensor, they must fit. And when we started, there was no metric, so we had to come up again with a novel metric to use this, and we did an analysis on a lot of available metrics or metrics that were used already, but none of them was fulfilling our requirements on the metrics in this case, because we needed a metric in the unit of the measurement to be able to actually specify the error. So in this case, for example, when you speak about distance values of the points, of the detections or the objects, then you need to specify, okay, I would like to have a simulation and it should only be different in the mean error and in the scattering in about, let's say, 10 centimeters or so. And you also need to have a metric that can handle probability boxes from multiple simulations, because you have to reflect your reference data accuracy by multiple simulations for the epistemic uncertainties that are inherent in this. So finally, we found a metric, and this is also possible to for example, consult our expert at the booth for this, or afterwards via email also. Next step, I mean, if you have different validation measurements done in your specified ODD, so the different parameters that will be available, you will have some samples from this parameter space, and you say, okay, for these parameters, for these samples, we took measurements, we can compare them against synthetic data, and in this case, it's valid. But it's not enough. You also need to know about what is about the rest of the parameter space where I have no samples for validation. So I somehow need to know, is my model still valid in this as well. And for this, the validity range actually cannot be guaranteed a priori. So, for example, in closed loop simulation, you start the scenario conditions, for example, different velocities, different distances to objects, different objects, materials, also environmental conditions, they can change. If you just have open loop, you can probably check beforehand if all the different parameters are still somehow checked beforehand and the model is valid for this. If not, you need to observe this. And monitoring model validity is then required. And a proof of concept of this implementation, in this case for vehicle dynamics, has been done in Z-level project. And the validity range in this case was defined by threshold values, internal states and variables. And there's a validity flex, a simple approach to output, okay, it's still valid or it's not valid anymore. And again, please visit the experts at the booth for this. So the next step, when we say, okay, we have all this done, we have the different models, we have validated them, we even know about their validity in the application, during application, we will combine different models. And what are the side effects of model coupling? So in this case, for example, you have an environment simulation. You have movement simulation of the different objects, you have vehicle dynamics, you have a sensor simulation, and you have the system under test, in this case, automated driving system, and you have closed loop. So yes, still, every model has kind of a parameter space where it's validated and it's fine, it fulfills the requirements, but what about coupling all these? And of course, it's not just a simple superposition and to say, okay, we know all of their validity areas, we can combine them. We have to investigate this. And especially when we talk about models from different developers, different sources, for example, provided as functional mockup units, as we did in this project, our black box system, you cannot look inside, you can just couple them, and you hope they are valid, or at least you should investigate if they are valid or not. And how can this done? This is a question that came up during the project. We did some first investigations, of course. You have different types of the model, so different coupling. So, for example, you have one model, for example, for vehicle dynamics, this is all in one FMU. And you have just to separate this into two, and we investigate. And of course, we find, okay, there are deviations. But in this case, it's not just small deviations, it's actually deviations that really matter during simulation. And this is a finding that is very important, and we want to stress here. Of course, we have the experts available today or even afterwards. You can contact them. And this is very important. So another aspect of simulation credibility. Again, we are not finished. We have a simulation platform running then. We need to qualify the tools. And tool qualification doesn't only mean you have synthetic data, you compare them against real data, or you have coupling. There's even more happening. So you have data management, you have a test automation. All this parameterization, also the visualization takes place. And all this is included in the tool. And there are further assessment categories even involved. Of course, there are standards available that tell you how to do this and what to consider, for example, the development process, the bug report handling, customer information, user manual. All this is also included in the tool and must be considered to have an overall credibility of your simulation. So let's come to the key takeaways. Of course, at first we showed it's a level-based approach for objectifying the credibility assessment, and exemplary creation of supporting artifacts has been shown by Nico. They are provided. Method library, exemplary validation, and credibility assessment reports are available. Then I showed exemplary sensor model specification and validation together with VV methods, of course. Validation metrics have been proposed, and they address the different uncertainties. Unwanted effects of model coupling have not just been estimated but also demonstrated, and are worth noting, of course, that there's a trade-off between IP protection, so black box FMUs, and validation of coupled models. Then I showed that there are standards for tool qualification. We have collected them, and this must be covered by the simulation credibility assessment layers as well. So thank you very much, and now we are open for questions.
Perfect. Thank you also very much.